All right, today we're talking about fractional exponents. In the past, if we had something like x squared, to undo the square, we would take the square root. That would give us x to the first. For example, 4 squared is equal to 16, but if you take the square root of both sides, you would see that the square root of 16 is equal to 4. Now, using the knowledge that we have now of our rules of exponents, we could go ahead and take our x squared and multiply it by 1 over 2 to get back to 1. 2 times 1/2 is 1. So the big idea for this unit is the square root of x is the same thing as x to the 1/2. Sometimes when you're solving these problems, it becomes easier to use a fractional exponent to simplify a radical than other things that you could potentially do. So let's remind ourselves how we simplify radicals. In the past, if we had something like, say, the square root of 100, we could simplify it by breaking it down into prime factors and then looking for pairs. So for example, we could take this one, split it down to say that 10 times 10 is equal to 100. Notice we have a pair of 10s, so therefore the square root of 100 is 10. Contrast that to something like the square root of 200. We could break this down into factors again, looking for, say, 2 times 100, which we could break down to 10 times 10. And we could reduce this to 10 radical 2. The pair of numbers goes outside the radical, leaving the number without a pair inside the radical. What this lesson is about is this works the same way with variables. So for example, if we had something like 4x squared underneath a radical, we could do the same thing we just did up here with the number. Take 4, split it into 2 times 2, put a 2 on the outside of a radical, but we could do the same thing with x squared. So for example, let's go ahead and split x into x times x for x squared. Notice, do we have a pair of numbers here? We do. We have a matched pair, meaning we can take that and write that outside of our radical. Now, similarly to how 4 times 4 is equal to 16, 2x times 2x would indeed give us 4x squared. So that kind of illustrates our point about this being the opposite thing. But what if we had something like 4x to the third? Well, once again, we could split the number down into 2 different parts. 4 becomes 2 times 2. And we could write our x's as x times x times x. I've broken this down to its most simple components that I can. Now we look for pairs. Look for pairs. We have a pair of 2's. We have a pair of x's, so I'm going to put one x on the outside of a radical. But you'll notice we have an x that has to be left behind. The same way we had to leave a 2 behind here, we have to leave an x behind here. So that is going to stay in the radical. Let's go ahead and try a more complicated problem. So for example, let's look at number 8 from the homework. The radical 16 x to the 4th, y to the 3rd, z to the 3rd. Let's start with the number. We've already discussed this in this particular video, that 16 is the same thing as 4 times 4, leaving us with a pair of 4's. So let's go ahead and put a 4 on the outside of the radical. We can break down our x to the 4th into a few more simple things. It could be x to the times x times x times x, 4 x's because of x to the 4th. That will give us one pair of x, so we can write an x on the outside. we can go ahead and write our other pair of x's on the outside. Another way of writing this, a little bit more simple, would be 4x squared. Now, every x had a pair. There are no x's left over to stay in the radical. Let's go ahead and try our y's. Y cubed, that's the same thing as y times y times y. We have a single pair of y's, so we can go ahead and add that to our answer. However, we have one y left over, so we're going to just go ahead and put that underneath the radical. We can do the same thing with the z's. Z cubed, that's the same thing as z times z times z. We once again look for a pair. We have a pair of z's, so that means one z goes on the outside, and one z has to stay on the inside because it doesn't have a pair. Let's go ahead and do another example. Let's try 108 u to the fourth v squared. Let's go ahead and break down our number into as simple as we can. Now, I can't necessarily think of two numbers off the top of my head that multiply to 108, so let's break it down into smaller pieces. So for example, I know that 108 is even, so it must have a 2. And 108 divided by 2, that's going to be 54. Now 54 once again is even, so let's go ahead and break that down. That's going to be 2 into 27. 27, that's going to be 3 and 9. Break down one more, it's going to be 3 and 3. So the prime factorization of 108 is going to be 2 squared, 3 to the third, or 2 times 2 times 3 times 3 times 3. From here, let's go ahead and see if we can see any pairs. Oh, I see that we have a pair of 2's, meaning I know that my answer must have a 2 on the outside. I also see that we have a pair of 3's, meaning we're going to have a 3 on the outside. 2 times 3 is 6. There must be a 6 on the outside. Now the one number that doesn't have a pair is that 3, so there must stay behind in the radical. Let's go ahead and look at our u's. I see once again that we have u to the fourth, so that means 2 pairs. U times u times u times u. We have 2 pairs of u's. That will be u squared. 2 pairs of u's means u times u outside of our radical. And we have v squared. That's going to be v times v, giving us a single v on the outside of our radical. And that is our answer. Now, sometimes we have things of other orders than square roots. So for example, lately we've only done x to the 1/2 is equal to the square root of x. But what's the opposite of, say, something like x to the third? There is such an operation. It's called a cube root, meaning it looks something like this. So that will give us in x by itself. We could have a cube root, which looks like so. Looks like a square root with the 3 added right there. That's called a cube root. You can have a 4th root. And so on and so forth. You can have any number here. So for example, this is a 5th root. And continue on just as many as you need. This is the same thing as x to the 1/3. It follows that this would be x to the 1/4. This would be x to the 1/5. And so on for whatever number that you need. These problems function identically to the other ones. However, the only difference is instead of looking for pairs like we did in the last, you're going to look for whatever number exists right there. So for example, if we did something like 24x to the 6th, but we're taking the cubed root of this, you would instead look for triplets, groups of 3 instead of groups of 2. So let's break that down. 24, we could rewrite that as 3 times 8. 8, that's going to be 2 times 2 times 2. That equals 8. Notice we have a group of 3 right here, a triplet. So that means in our answer, we're going to have a 2 on the outside. However, the thing that doesn't have a triplet has to stay behind, so that's going to be our 3. Now we have x to the 6th, so that's x times x times x times x times x times x, 6 of them. We have 2 pairs of triplets, so that's going to be x squared, giving us an answer of 2x squared radical 3. Last thing I forgot is make sure that you keep the little 3 right up there to say it's a triplet. This has to match your answer. We could do higher powers than this. So for example, we could do the 5th root of 64 n to the 10th m squared. Let's go ahead and do that. Well, let's go ahead and first break down 64. I know that that's going to equal 2 times 32. 32 is equal to 2 times 16. 16 is equal to 2 times 8. 8 is equal to 2 times 2 times 2. So looking here, we have a group of 5 2's, meaning in our answer, there's going to be a 5 on the outside. Oh, sorry, I lied. Got my numbers confused. There's going to be a 2 on the outside, and inside the radical, there's going to be a 5 and a 2. Without writing out all the n's, we have 10 of them. I'm thinking in my brain, if we have 10 n's and we're breaking them into groups of 5, that means we're going to have 2 complete groups of n. So that means we're going to have n squared on the outside. So n times 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 n. 2 complete groups of 5. M squared here, that's just m times m, so that we don't have enough for a group of 5, so that means that has to stay within the radical. So as a general rule, if there's nothing outside the radical, look for pairs. If there's a number, look for groups of that size. Also, one last detail, multiply numbers. We did an example of that right here. When we did 108, we had 2 times 3 on the outside. We multiplied those numbers together. Let's go ahead and do one last example problem. Let's do the 4th root of 162 m squared into the 5th. Let's go ahead and break down 162. That's going to give us 2 and 81. 81, that's going to equal 9 times 9. 9 times 9 is going to be 3 times 3 times 3 times 3. You'll notice we have a group of 4 3's. So that means there's going to be a 3 on the outside. What stays inside the radical? The 2. It doesn't have a pair. M squared also has to stay inside the radical because there's only 2 m's. That means we don't have a group of 4. However, we have a group of 4 n's. So there's going to be 1 n here. However, there's going to be 1 n left over because there's only 5. So that's going to stay on the inside. As always, let me know if you have additional questions.